In the last class we are discussing about the 8086 signals and pins. So, we have discussed about this common 32 signals and then 8 exclusive signals for the minimum mode configuration. So, there are 8 exclusive signals for the maximum mode configuration. So, the 8 signals are S2 bar, S1 bar, S0 bar. So, the function of this one will be for 0 0 0. So, it performs interrupt acknowledge operation. So, whenever an interrupt occurs to the microprocessor, so during the acknowledgement of that particular interrupt, S2 bar, S1 bar and S0 bar will be 0 0 0. If this is 0 0 1, then this represents IO read operation. So, we know that we have microprocessor can perform 4 microprocessor initiated operations. So, out of these 4, one is memory read, IO write, IO read. Okay. So, for 0 0 1 this is IO read. For 0 1 0 this is IO write. For 0 1 1 this is halt operation, and for 1 0 0 this is code access, it accesses the code. 1 0 1 memory read, here this is IO read, whereas here this is memory read. 1 1 0 memory write. Whereas 1 1 is not used. So, this is the function of the 3 maximum mode signals S2 bar, S1 bar, S0 bar, they are active low signals. Then coming for the other signals, so we have Q status 1, Q status 0 signals. So, QS stands for Q status. So, we know that we have already discussed in the architecture, 8086 contains 6 byte instruction queue. So, by using this instruction queue we can overlap the fetch and execute operations, thereby you can increase the speed of the operation, which is called the pipelining. So, the status of this queue will be indicated by this QS1 and QS0. So, the 4 combinations of the QS1 and QS0, the corresponding operations are as follows. 0 0 represents the first byte, read the first byte, which is called opcode fetch, that is opcode fetch from Q. So, always you take any instruction, the first byte will be opcode fetch, the code correspond to each instruction. For example, if I write say for example move AL comma CL. So, correspond to this move there will be a code which is called opcode. So, this is fixed for this 8086 microprocessor, there is a format to generate that code opcode. So, always in order to execute any instruction, the first byte will be the opcode, the next byte will be the registers, or it can be data, it can be address. So, when this QS1, QS0 are 0 0, it reads the first byte which is by default opcode fetch from the instruction queue. 0 1 it empties the queue. One zero is not used. 1 reads the subsequent bytes from the queue. Is this after this first opcode fetch, then it may require the subsequent bytes. There are some instructions where only this opcode fetch is there. So, in that case it will not read any subsequent bytes. So, this is about the queue status signals. So, we have discussed about the 5 signals. So, remaining 3 signals of maximum mode operation of 8086 are, there are 2 signals called request by grant 0 and request by grant 1. This RT stands for request, GT stands for grant. So, we know that in case of maximum mode operation, it is a multi-user configuration. So, several users can use the same microprocessor. Suppose if I have 8086 microprocessor, suppose if any external bus master this want to use the address buses, data bus in general, the system bus which is called as system bus. Together address bus, data bus is together is called as system bus. So, whenever this bus controller or bus master, external bus master wants to use the address and data buses of this 8086 microprocessor, it will request through one of these signals. Either this can be any one of these signals, through these signals it will request. So, in order to request this, what it will do is, it will send one clock duration pulse. Will be sent on this line. So, this can be request by grant 0 or request by grant 1. So, when what happens is, between these two, the RT by GT 0 is having higher priority than the other one. So, whenever the request, simultaneous request comes on both the signals, then this RT by GT naught will be served first, that is meant by the higher priority. So, whenever this bus master requests through this RT by GT bar through one clock duration pulse, this should be one clock duration pulse, then what this microprocessor will do is, it will complete the execution of the current bus cycle, current operation. After that, this will inform this bus master through this same signal, using one clock duration pulse, saying that the 8086 is going to relinquish the system bus to the bus master. This is after the completion of the current bus cycle. 8086 sends one clock duration pulse to bus master, indicating that the system bus means both address and data bus control is relinquished. Now the bus master can use this system bus for its own purpose. So whenever this data transfer is over, after the data transfer is over, the bus master sends active low signal on RT by GT. This can be RT by GT0 or RT by GT1. After that, the 806, then the 8086 regains the control of system bus. This is the complete process which takes place for request by grant 0 or request by grant 1 by external bus master. So while requesting, it will be one clock duration pulse. Similarly, the acknowledgement will be on the same line. This is bidirectional. So on the same bus, the 8086, after completion of the current bus cycle, it will again send one clock duration pulse to the bus master, indicating that the control of the system bus is relinquished to the bus master. Now the bus master can use the system bus for transferring of the data. Once the transfer of the data is over, then the bus master will send active low signal. It is not one clock duration, okay, it is just for only for short duration. So a low signal on the same RT by GT line. So then the 8086 regains the control of the system bus. This is the entire process for requesting the system bus of 8086 by the external bus masters. So between these two, RT by GT naught will be having higher priority. Okay. So if both the request come simultaneously, the 8086 grants RT by GT0 request. So while the bus master is requesting this, so the other bus master, to avoid the other bus master to request for the system bus, we have another signal which is maximum mode signal, which is called lock bar signal. A low on lock bar signal indicates that the request of the other bus master is not granted. Is prohibited. Means already, so this 8086 is processing the request of one bus master. So at that time, if another bus master requests for the system bus, it simply places a active low signal on the lock bar signal, indicating that bus master, that the second bus master, that the request is prohibited until the service of the first bus master. Once the first bus master uses the system bus, and after the data transfer, it will give the control to the 8086, that time lock bar signal will be high, so that the second bus master can request for the same system bus. So these are about these three signals, RT by GT naught, RT by GT1 and lock bar, and we have here 5 signals, S2 bar, S1 bar, S0 bar, QS1, QS naught. So this is about the maximum mode signals of 8086. So, we have discussed about the complete architecture of 8086, the functions of all the signals. Okay. So, this is what about this architecture of 8086. Then coming to the second portion of this course. So, one portion is architecture, then instruction set. Using this instruction set we can write some programs, starting from simple programs to some complex programs. Later the third part is how to interface the external devices such as IO and memory, how to interface to the 8086. So, this total course is divided into three parts: architecture part, then instruction set followed by the programming, then interfacing. So, now coming for this instruction set of 8086. So, the total instructions of this 8086 can be divided into several categories. So, like we have this data transfer group, arithmetic group, logical group, some string operations. First I will start with the data transfer group. The data transfer group of instructions. So, in the data transfer group, one of the important operation is move operation, move instructions. The general format of a move instruction is, we can have the mnemonic will be, the code will be move, MOV. So, here we will be having register slash memory 2 comma register slash memory 1. Simply here the operation will be the contents of register slash memory 1 will be transferred to the contents of register slash memory 2. So, in microprocessor terminology, this represents, this square bracket represents contents of. So, here there are some 4 possibilities: register to register, register to memory, or memory to register. The fourth combination is not allowed. Memory to memory transfer is not allowed. Data transfer from memory to memory, memory 2 to memory 1 is not allowed. So, for that you have to transfer the memory contents into some register, then from register to again another memory. So, direct transfer of the data from one memory to another memory is not allowed using this instruction. Whereas there are some string instructions where we can transfer a string of the data from one set of the locations to other set of the location, that I will discuss later. So, here always the first register or memory will be destination and this will be source. So, if I take some examples, so we have 3 possibilities here as I have told: register to register, memory to register, or register to memory. Okay. So, if I take example, all the examples, move CL comma BL, this is register to register. So, if before the execution of this instruction, if CL contents is 35H and BL contents is 99H, simply the contents of BL will be transferred to CL, means CL contents becomes after this 99H, but BL contents remains same 99. So, here this particular instruction belongs to a register addressing mode here, because both source and destination are registers. So, later I am going to summarize these addressing modes. This is called register addressing mode. Here both are registers. This is 8-bit registers, we can have 16-bit registers also. Move DX comma AX. So, simply the contents of AX will be transferred to the DX. The contents of AX remains same. So, these are the examples of register addressing mode. We cannot transfer 8-bit. So, one between this source and destination, one is 8-bit register, another is 16-bit register. This is not possible. The size of both the registers must be same. So, in memory to register to register data transfer, the sizes of both the registers must be same. Coming for the second possibility, this is register to register. The second possibility is we can transfer from memory to register or register to memory. I will discuss both. Move register to comma memory, or you can have move memory to register. Now, how to represent the memory? Registers we have different combinations. We have 8-bit registers such as AL, AH, BL, BH, okay, CL, CH, like AX, BX, DX. We have different registers. What about the memory? Memory we can have 1 megabyte of the memory, total memory. Now, from each memory location you want to transfer the data to the register. So, we can represent this memory location in different ways. So, depending upon this one, so we have different addressing modes. So, the memory can be directly we can represent in the instruction itself using data segment. So, the examples of this different this memory to register transfer or register to memory transfers will be, if I write something like move AL comma, if I write DS, some start is to DS or DS is to start. So, here in all this memory that this all move instructions, by default the segment register will be DS. So, by default the segment register will be DS here. Here default segment register will be DS and none of the flags will be affected here. Okay. You can write here that. So, for this move instruction none of the flags will be affected. And segment register is DS. These are two important points for move instruction. So, here what happens is start is a offset. This we have to define by using assembler directives. So, initially we can assign this some value to the start. Say let start is defined as is equal to some 0040H. If the contents of DS, so we know that DS is a 16-bit register which holds the upper 16-bit starting address of the data segment register, which is called effective address. If this is say some for example 5000H, then the physical address, this is called effective address. Effective address is always 16-bit. Then 20-bit physical address will be I will call as PA. Will be, we know that we have already discussed in the earlier classes, 5000 into 10H is the just DS segment. This will be equal to 50,000. So, if you have the start value of 0040H, the meaning of this one will be the address from where the memory location from where the data will be transferred to the AL. This is basically this transfer the data from memory location to AL. This is memory. Which memory location? What is the physical address of that memory location? To compute this, so what is the data segment contents is 5000. So, the physical address will be 50,000 plus you have to add start. The meaning of this one is data segment physical address plus start value. So, plus if I add start value which is equal to 0040. So, the total address becomes 50040H. Now this instruction, if the contents of 5000H is 50040H is this 8 bit some F2H. Then after the execution of this instruction for this particular data, so after the execution of this instruction AL will be loaded with F2H. For example, if I write here, instead of writing AL, if I write move AX comma the same thing, say DS slash start. If I assume the same values of DS and start, then what happens is here, because the destination register is a 16 bit register, if the destination register is 8 bit register, it will just simply read a byte from this location. If the destination register is 16 bit register, it will read a word is nothing but 2 bytes. So from which location, so the whatever the first location that we are going to get, that will be transferred to AL out of AX. So we have 2 parts, this is AL and this is AH. So this contents F2 will be transferred to AL. The contents of this 50041H, let this is something like 3E, this will be transferred to the AH. Depends upon destination register is 8 bit or 16 bit, it will read a byte or word from the memory locations. So the starting location will be this, if it is a byte only, this contents will be transferred to that particular destination 8 bit register. So if this destination register is 16 bit register, it will take 1 byte from here, it will transfer to the lower order register of that 16 bit register, and this address plus 1 contents will be transferred to the higher order 8 bit register of that AX 16 bit register. So this is about this address. So this actually this belongs to a direct addressing mode. Here in case of direct addressing mode, the address of the memory location will be specified in the instruction itself. The register which contains this address is specified in the instruction itself. This is one way to represent the memory. So in any case, it can be from memory to register or register to memory. Okay. So how to represent the memory location depends upon the way in which that we are going to represent the memory location, access the memory location, compute the memory location. We have different addressing modes. This is direct addressing mode, where the address of the memory location can be computed by taking the DS contents, then multiply with 10H, then add that start value which can be defined by using a assembler director in the program. So that will be the physical address, 20 bit address. So from this you have to transfer a byte or word depending upon whether the destination register is 8 bit or 16 bit. So this is about direct addressing mode. There are several other ways to represent the memory. The second way to represent the memory is this can be from either register to memory or memory to register. AL comma, now I will specify the contents of some BX register. Now what will be the operation? So in order to compute the physical 20 bit physical address here, so what is required is, so if I assume that before the execution of this instruction, if the contents of data segment register is say some 5000H and the contents of BX is some 2000H, then the 20 bit physical address will be computed. Physical address is given by now 5000 into 10H plus the contents of BX, which is 2000. So this will comes to 52000H. This is the 20 bit physical address from where the contents will be transferred to the AL. If I assume that the contents of 52000H here will be some 2C, Then after the execution of this instruction, the contents of AL will be 2C. Suppose if I write move AX comma BX, contents of BX, if the contents of the next address is 52001 is some value 3 2 say, then after this the contents of AX becomes 2C will be the lower contents and for 3 2 will be the contents of AH. This is similar to the previous example. So, here the address is not specified, data segment by default it is there, but here you have specified some base register, that is why this particular addressing mode called register indirect addressing mode. So, in this we are going to specify the register which contains some address. Okay. So, from that address we are going to offset of the address, of course offset of the memory location, from that physical address we are going to transfer the data indirect, whereas in the previous case directly we have specified the data segment in the instruction itself. So, this is from memory to register, you can perform in a similar manner register to memory also. In the same register indirect addressing mode, if I write something like move BX comma AL, if I assume the same values of the registers and data segment register and the other registers, then the operation that will take place here will be, if I assume that AL contents is here some DD H. So, if I write this, the physical address is 5200. So, after this instruction what happens is 52000 will be loaded with the contents of AL, which is before the execution of this one I am assuming that DD. Okay. So, this can be either from the memory to register or register to memory. If it is 16 bit, move BX comma AX, if AL is this one, if AH is also, I am writing here same thing AH and AL, which is AX, if AX contents is something like AL, if I assume that same DD, if I assume that this is BB, then after this what happens is 52000H will be having AL contents which is DD, same as the previous one, then this place one address, this place one which is 52001 will have AH contents BB. So, these two are the examples of register indirect addressing mode. In one case the transfer is from memory to register, in other case it is from register to memory. So, here one thing that you have to remember is the register that we are going to specify here. So, this register can be, this can be one of these four, it can be BX, BP, SI or DI. So, in addition to BX, BX is a general purpose register which can be used to store the data like AX. In addition to that the general purpose of BX, BX also will be used as a base register in address calculations of this register indirect addressing mode. So, the possible registers here will be BX, BP which is base pointer, I have discussed it in this architecture, source index or destination index. Then coming for the another example, this move instruction is a very useful instruction in 8086. We can write several programs using move instruction. So, this is a very strong instruction. So, we have lot of combinations here. So, if I use another move instruction, so this depends upon the how we are going to specify the memory address. If I write something like move AL comma contents of start VX, we can write. Then how to compute the physical address of this memory location? So, by default always you have to use data segment only. Data segment if it is 5000, and if the start value is some 0040H, this has to be defined by the user by using assembler directive, and if the contents of Bx is some 3900 say. So, we know that all these registers are 16-bit registers, they contains only effective address. Then the physical address will be computed using ds into 10 plus start plus Bx. So, this will come to here. So, this will be 50,000 plus 0040 plus 3900. So, which will be 50,000 0040 3900. This will be 40935. So, this is the physical address of the memory from where the data will be transferred. Now, if the contents of this location is 53940 is CC, then after the execution of this one AL contents becomes CC. So, this type of addressing mode is called based addressing mode. So, in this, so we are going to write some offset, then base register. This register can be here either Bx or Bp only. In case of based addressing mode, the offset will be present in the registers either it is Bx or Bp, and this start, this also can be written as in assembler directive. This instruction is same as move AL comma start Bx is also same as this is equivalent to move AL comma, we can include this inside this Bx plus start. So, these two are one and the other same. While writing the assembler directives, you have to write in this manner. Okay. So, similarly you can have this destination as AX, then this location plus another location contents will be transferred to AX. So, if it is from register to memory, again the contents of this will be transferred to this location. If it is AL, if it is AX, contents of AL will be transferred to this, AH will be transferred to this place another memory location. So, here we can have source can be either register or memory, destination can be either register or memory. So, this is called based addressing mode. So, there is another addressing mode where indexed addressing mode, same thing, but here instead of base register we will use index register. So, this can be here either SI or DI, source index or destination index. This is called, this type of addressing mode is called indexed addressing mode. And also same thing, now the physical address will be computed in a similar manner. I am not going to give the example, same thing. So, ds into this plus start plus here instead of Bx it will be contents of Di. We can compute this physical address, from that address the data will be transferred to AL if the destination register is 8 bit, if the destination register is 16 bit. So, this physical address contents will be transferred to AL, this plus 1 will be transferred to AH. So, the only difference is here instead of using base register we will use index register, whereas in the previous addressing mode, register addressing mode, this register index addressing mode, this can be all the 4 either Bx, Bp, but here there is offset. whereas in these applications we have offset start, here also start and start. So, another example is you can use both also, which is called based index addressing mode. So, if I write say move AL, here also you can write this as DI plus start. So, this can be either BX or BP, this can be SI or DI. Now, here what is the physical address, how to compute the physical address? If I take this values, start value is this, DS is this, BX is this, DI is say for example 9000 say, then what is the physical address from where the data will be transferred to the AL. So, in all these move instructions we are going to discuss about the different ways to access the memory location, which memory location, how to compute the memory location, physical address of the memory location. So, this is clear that the physical address will be now here similar to this DS into 10H plus start plus BX plus DI. So, up to this we have already computed, which is 53940H, 53940H plus only extra additional term is here DI content is 9000. So, this will becomes now 53940 plus 9000, this will be 0 4 9, 9 plus 3 is 12, in hexadecimal 12 is represented by C. So, suppose if the before the execution of this instruction contents of 5C940 is AA. So, after the execution of this is 5C940. After the execution of this instruction, the contents of AL becomes the contents of this memory location, which is AA. This is about based index addressing mode. This stands for based index addressing mode. So, these are the different way to represent the memory location, to transfer the data from either register to memory or memory to register. Okay. So, in any case, how to compute that memory, the memory address, there are different ways. We can compute using only the data segment that is given here, then we can add some offset, or we can compute from using base registers or index registers, only base registers and displacement, index register plus displacement, base register plus index register plus displacement. This is to compute the physical address of the memory, and register will be specified in the instruction. Register can be either 8 bit or 16 bit. Okay. So, these are all about the move instructions, and we can have move string operation also. So, the next move instruction is move string byte. There is no memory, there is no address, okay, there is no register, there is no memory. So, directly move string byte. This of course I have explained while while discussing about the directional flag. Okay. So, this move string byte by default it will assume that the number of bytes to be transferred from source to destination. This is a string operation basically. This belongs to string addressing mode. Means if you want to transfer an array of data from some set of locations to another set of locations. So, this is say source, this is destination. So, I want to start from this location, I want to transfer some number of data to this destination locations. So, I want to transfer this contents to these contents, this to here, this to here and this to here. Let us assume some locations, say this is some 60,000 H, and this will be 60,001 H. First to decide how many bytes you want to transfer, what is the length of the array, length of the string or length of the array. Let length of the array is string is equal to 100 decimal. So, this will be 64 hexadecimal. So, I want to transfer 100 bytes starting with this address to this destination. Say destination, this address is 70,000 H, this is 70,001. So, in the last address will be total I want to transfer 64 H locations. In decimal this is 100, hexadecimal if you want to convert the decimal to hexadecimal it will be 64 H. So, starting with 0 the ending address will be 60063 H, because 0 is starting point, ending will be 1 less than this. So, the above address will be 60062 H, and this will be 70062 H, and this will be 70063 H. So, I want to transfer 100 bytes starting with 60,000 of this source and destination starting address is 70,000, and I want to transfer the data from top to bottom. Okay. So, I want to decide whether this is from top to bottom or bottom to top. So, total I want to transmit 64 kilobytes. So, if I write simply move string byte, so before this we have to specify something. Okay. What is that is, before this instruction you have to, by default this 64H has to be taken into only CX register only always in string operations. So, CX in addition to this general purpose operations of CX, CX also will be used as a counter register in string operations. Okay. So, you have to load this 64 onto the CX 0064H. So, because CX is 16 bit register, whereas this is 8 bit data, the remaining two I have added 00, means the maximum number of the bytes that can be transferred will be FFFFH. This is the maximum capacity of the bytes that can be transferred from here to here, that is 64 kilobytes of the data can be transferred from one set of the locations to another set of the locations using the string instructions. So, by default the number of bytes to be transferred has to be taken into CX register. Okay. Then we have to either set or reset the clear flag or direction flag. So, you have to write either CLD clear direction flag. This is the instruction that I am going to discuss later, but this is a simple instruction. This simply clear direction flag. CL stands for clear direction flag. STD stands for set direction flag. So, if the direction flag is set, then this will be from top to bottom. If direction flag is reset, this will be from bottom to top. Okay. So, this will be bottom to top, because this is bottom to top, 6000 is bottom value. So, top value is 630. So, you have to clear the direction flag. So, simply you have to write here before this CLD, and to load this 0064H, this also have not discussed, this is immediate addressing mode. So, we can use directly move CX comma 0064H. This will comes to the immediate addressing mode. We can take either 16 bit or 8 bit data, directly you can transfer to the either 8 bit or 16 bit register. Here, because this destination is 16 bit, you have to take 16 bit immediate data. If the destination is 8 bit, we have to take only 8 bit data. Okay, this is another move instruction that I have missed there. So, this will be immediate addressing mode. So, I can write here simply this operation is nothing but move CX comma 0064. So, these three instructions are enough, then automatically the contents of this will be transferred to here, this will be transferred to here, this to this. So, on up to 60063H to 70063H. So, by simply writing the three instructions, a string of data will be transferred. This is what is called move string byte. Similarly, you can transfer even move string word also. There is another instruction which is called as, so this belongs to the string addressing mode. So, this is one instruction. Another instruction is, we can write move string word. B stands for byte, which is equal to 8 bits. W stands for word, which is 16 bit or 2 bytes. So, everything is same. Here also we have to set the CX to the some value, the number of bytes to be transferred, number of words to be transferred now here. In this case, number of words to be transferred. If I want to transfer same 100 decimal words or 64 hexadecimal words. So, then you have to load into CX register, then you have to clear the direction flag if you want to transfer from. So, the source index and destination index. So, here in this case, this address will be pointed by this upper 16 bit starting of this will be pointed by source index, and this upper 16 bit destination address will be pointed by destination index registers. So, after the each byte, the contents of the source index and destination will be automatically incremented if the direction flag is cleared. If direction flag is set, they will be automatically decremented. So, that is how this 100 will be transferred. Here also same clear direction flag, then you have to write move string word. So, instead of this move string byte, if I write move string word, then what happens is this will take 2 bytes. So, these 2 bytes will be transferred to these 2 bytes. So, totally this will take 200 bytes will be transferred from source to destination. So, this will be this is source and destination, same example, but here the number of bytes will be transferred is it's 100 words, because I have written move string word and I have loaded CX with (0064H), then I have cleared the direction flag. So, 100 words has to be transferred. So, 100 words is 100 decimal, 100 words is equal to 200 bytes. In hexadecimal, what is this 200 bytes? 100 is equivalent to 64. How to convert this decimal number to hexadecimal number? You have to divide with 16. 6 ja 96, 4, 16 zeros, 6. So, that is why this is 64H. 100 decimal is equal to 64 hexadecimal. Now what is 200 decimal? 200 12s, 16 12s will be 192. So 16 12s 192, remainder is 8, 16 zeros, remainder is 12, which is called as C. So this is equal to C8. So this is equal to C8H. So if I start here, this has, so what is the address that I have taken here before? 60,000 and 70,000. So 60,000 H, 60,000 1H, then the last address will be C8 means 00 to C7, 600 C7 because starting with 0. This will be 600 C6. So totally 200 bytes or 100 words will be transferred. This will be 7000 0H, 7000 1H, so on up to this is 700 C6H, 700 C7H. This is how we can transfer either bytes or words. Here also this source and destination will be pointed by this. This is how you can perform move string byte or move string word. So these are some data transfer instructions. So we have some other instructions like push and pop, XLAT. So the remaining data transfer instructions we will discuss in the next class. Thank you.